Why won't the supernova explode? Presented by Science at NASA. Somewhere in the Milky Way, a massive star is about to die a spectacular death. As its nuclear fuel runs out, the star begins to collapse under its own tremendous weight. Crushing pressure triggers new nuclear reactions, setting the stage for a terrifying blast. And then, nothing happens. At least that's what supercomputers have been telling astrophysicists for decades. Many of the best computer models of supernovas fail to produce an explosion. At the end of the simulation, gravity wins the day, and the star simply collapses. Clearly, physicists are missing something. We don't fully understand how supernovas of massive stars work yet, says Fiona Harrison, an astrophysicist at the California Institute of Technology. To figure out what's going on, scientists need to examine the inside of a real supernova while it's exploding. Not a particularly easy thing to do. So instead, they examine the remnant of the exploded star as soon after the explosion as possible. Harrison and colleagues have figured out how to do this using a new space telescope called the Nuclear Spectroscopic Telescope Array, NuSTAR for short. Launched on June 13, 2012, on board a Pegasus XL rocket dropped from an airplane high above the Pacific Ocean. NuSTAR is a small explorer satellite that carries the first space telescope that can focus very high-energy X-rays. NuSTAR will produce images roughly 100 times sharper than those possible with previous high-energy X-ray telescopes. When NuSTAR finishes its checkout and becomes fully operational, scientists will use it to scan supernova remnants for clues etched into the pattern of elements spread throughout the explosion's debris. The distribution of the material in a supernova remnant tells you a lot about the original explosion, says Harrison. An element of particular interest is titanium-44. Creating this isotope of titanium through nuclear fusion requires a certain combination of energy, pressure, and raw materials. Inside the collapsing star, that combination occurs at a depth that's very special. Everything below that depth succumbs to gravity and collapses inward to form a black hole. Everything above that depth will be blown outward in the explosion. Titanium-44 is created just above the cusp, so the pattern of how titanium-44 is spread throughout a supernova remnant can reveal a lot about what happened at that crucial threshold during the explosion. And with that information, scientists might be able to figure out what's wrong with their computer simulations. To detect titanium-44, NuSTAR needs to be able to focus very high-energy X-rays. Titanium-44 is radioactive, and when it decays, it releases photons with an energy of 68,000 electron volts. Existing X-ray space telescopes, such as NASA's Chandra X-ray Observatory, can focus X-rays only up to about 15,000 electron volts. Normal lenses can't focus X-rays at all. Glass bends X-rays only a minuscule amount, not enough to form an image. X-ray telescopes are an entirely different kind of telescope consisting of many concentric shells. They look a bit like the layers of a cylindrical onion. Incoming X-rays pass between these layers, which guide the X-rays to the focus by reflecting them off the surfaces of the shells. The NuSTAR team has spent years perfecting delicate manufacturing techniques required to make high-precision X-ray optics for NuSTAR that work at energies as high as 79,000 electron volts. Their efforts could crack the mystery of the supernova that wouldn't explode. And that's just for starters. NuSTAR will also study black holes, blazars, pulsars, and many more exotic objects. The high-energy universe is about to come into sharper focus, and no one can say what surprises may be in store. For more explosive information about the cosmos, visit science.nasa.gov.